Hello students. So let us continue with chapter 11, work and energy. Now in the previous video you have studied what is energy. You have seen the definition and its SI and CGS units. You know there exist various forms of energy. Now in this chapter we are going to study two types of energies in detail, kinetic energy and potential energy. We are going to derive expressions for these two kinds of energies. And the sum of kinetic energy and potential energy, as mentioned in the previous video, is called as mechanical energy. So let us first see what is kinetic energy. Now you know anything which is moving, this we have discussed last time also, any body which is in motion has energy due to its motion. And this energy is called as kinetic energy. You consider running train, flying bird. There are so many examples. Anything in motion you consider, you know that it can do work. It can do work means it can apply force, it can displace the bodies, and hence W is F into S. It can do work, and so when a body can do work, it has energy. So the energy possessed by a body due to its motion is called as its kinetic energy. So kinetic energy is the energy possessed by a body due to its motion. You can write possessed by a moving body, that also will be fine. But in case you write the definition like this, kinetic energy is the energy possessed by a moving body, you will not get marks for the answer because moving body may have different forms of energies. Okay, so you have to write that kinetic energy is the energy possessed by a body or a moving body due to its motion or by virtue of its motion. In case you don't write this, your definition will go wrong. So if I ask you what is the SI unit of kinetic energy, you know the answer. SI unit is Joule and CGS is erg. Because all forms of energies, they have the same unit only, Joule and erg as SI and CGS units. Okay. So here I have written examples of bodies having kinetic energy. Flying bird, running car, a rolling stone, flowing water, blowing wind, falling coconut, etc. has kinetic energy. Now when we talk about these objects or these things in motion, here when we say a flying bird, you will see later on that flying bird example can be given for kinetic as well as potential energy, that we'll see later on. A car running on a horizontal road has only kinetic energy. A rolling stone which is rolling on the ground has only kinetic energy. But if the same stone is rolling from the any height or along the surface of the mountain, let us say, then it has both kinetic and potential energy. We'll see it later on. Similarly, we can talk about other moving objects also. So when the moving objects are on the ground, okay, then they have only kinetic energy. And I think so I have discussed a little bit about gravitational potential energy in the previous video. So anything which is at height and in motion has both kinetic and potential energy. So here we can say, now you know blowing wind. You know blowing wind, wind energy farms are there which use the energy of blowing wind or which uses wind energy to generate electricity. Similarly, flowing water, the energy of flowing water is used in hydroelectric power plants to generate electricity. You know that a coconut when it falls, suppose if it falls on your head, just think the work it can do on your head. But at the same time, when we know that anything in motion, we have experienced and you see in day-to-day life that bodies in motion have kinetic energy. But think about a falling coconut and compare it with a falling grape. So when you compare a grape and a coconut, if both are falling from the same height, you know who can do more work? Coconut. Similarly, when we talk about a running car and a running train, who can do more work? A running train. So from this we can say that kinetic energy must depend upon mass of the bodies. Okay, so for a given body, it depends upon its mass. Similarly, if you think about a car running at speed of 50 km per hour and a car running at speed of 100 km per hour, you know, a car which is running at 100 km per hour can do more work and thus more harm also. Similarly, if the wind has more energy, more speed or velocity, then it has more energy. It means, so from these things you can make a guess. You know that if I ask you the factors on which kinetic energy depends, you can easily say kinetic energy of a body depends upon its mass and its speed, or we can say magnitude of velocity. But how it depends, what is the formula, that we don't know. But at least we can answer that mass and speed or magnitude of velocity are the two factors on which kinetic energy of a given body depends. Now let us derive an expression for kinetic energy. Let us derive the formula for kinetic energy. So first we'll write the introduction part. Consider a body having mass m moving with initial velocity u on frictionless surface. We can write frictionless horizontal surface. Let a constant force F be applied on it for time t, so that its velocity becomes v and s is the magnitude of displacement covered in time t. You can add here that s is the magnitude of displacement covered in time t in the direction of force applied. So I have already told you that in our syllabus, generally we consider that displacement produced is always acting in the direction of force applied. So even if you don't mention, we will assume that force and displacement are in the same direction. Now, for derivation, what we know that work and energy are equivalent. So if a body is moving with some velocity u and we do work on it, so whatever work is done on the body will be equal to change in its, in this case it will be equal to change in its kinetic energy. So work done is, if the body is initially at rest, instead of u, the body is initially at rest, it means u is 0. Then we can say whatever work is done on the body to make it move and to attain some velocity, then that work done will be stored in the body as its kinetic energy. So after writing the introduction, we know that we are going to find out the work done to make the velocity v from u to v of this body. So if w is work done on the body, w is equal to f into s. Number it as 1. Now it's simple, it's a very simple derivation. For f, you use the second equation of Newton's second law of motion. So using F is equal to ma. I have not introduced a here. You can write where a is the acceleration produced, or you can mention in the introduction also that a is the acceleration produced in the body. Okay, or you can mention it here when you write using F is equal to ma. And you use the third equation of motion. V square is u square plus 2as, and from this you get the value of s. That is not the value, the expression for s. S is equal to v square minus u square upon 2a. So what I have done here, I have used Newton's second law of motion for getting the expression for f, and I have used the third equation of motion to get the expression for s. Now putting these two expressions for f and s in equation 1, we get w is equal to, f is now ma into s is v square minus u square upon 2a. A will get cancelled. Okay, and as I have told you, if u is 0, if we consider initially the body is at rest, then putting u is equal to 0, this is 0, then this work done will become half mv square. We have considered if the body is initially at rest, then work done is half mv square. And so just mention this, that the work done is stored in the body as its kinetic energy. Therefore, kinetic energy of the body is equal to half mv square. I hope the derivation is very simple and you have understood this. Now you just can do one more question with the same method. You know, work energy principle is there. Work energy theorem or work energy principle. What it says that whenever work is done on the body, that work done is equal to change in its mechanical energy. But in this case, we are assuming that the body is moving on frictionless, as I have told you, horizontal surface. So then potential energy will not change, as horizontal surface means potential energy, whatever it is having, it is going to remain same. And we can consider it to be the ground also. For ground level, potential energy is considered to be zero. I am talking about gravitational potential energy. So in this case, when the body is having zero gravitational potential energy and it is moving on the ground only, we can consider work done on the body is equal to change in its mechanical energy, that is change in its kinetic energy. So if I ask you to prove the work energy theorem, you will follow the same method. You will first write the statement. Work energy theorem states that work done on a body is equal to change in its mechanical energy. And in this case, we are proving that work done is change in its kinetic energy, because potential energy does not change or it remains zero. Same introduction, everything same. Only one step difference will be there. What is that difference? Here, when you get W is equal to M by 2 into V square minus U square, don't take U is equal to 0. When you don't take U is equal to 0, this W will be, when you open the bracket, this W will be half mv square minus half mu square. So half mv square minus half mu square. Half mv square is what? Final kinetic energy. And half mu square will be initial kinetic energy. So we can write W is equal to final kinetic energy minus initial kinetic energy. So W is equal to change in its kinetic energy. And hence work energy theorem is proved. So using this, you can derive an expression for kinetic energy of a body, and just same method, just don't take U is equal to 0. We can prove the work energy theorem in case the body is changing only its kinetic energy. Now from here, if I ask you at the end, what are the factors on which kinetic energy depends and how? We can easily answer that kinetic energy depends upon two factors, mass of the body and its speed. How? Kinetic energy is equal to or is proportional to, directly proportional to mass of the body, and it is directly proportional to V square, square of its speed or square of the magnitude of velocity. And SI unit will be joules. So from here we can easily, so today's you should be able to, after watching today's video, you should be able to answer to these questions. Define kinetic energy, state its SI CGS units, give examples of bodies having kinetic energy, derive an expression for kinetic energy, state work energy theorem, prove it, and derive an expression for kinetic energy. State the factors on which kinetic energy depends and how does it depend. We'll continue with this chapter in the next video, where we'll see the same things for potential energy. I hope the video is clear to you. Thank you, students.